This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll examine several illustrated examples of parallel DC circuit analysis. This lecture operates under the presumption the viewers survive the Parallel DC Circuit Examples Level 1 lecture with their sense of dignity still intact. If you haven't watched this lecture yet, by all means take the time to do so now and return to this lecture when you are so qualified. You note the problems in the aforementioned Parallel DC Circuit Examples Level 1 lecture were total setups, so easy that even a snowboarder could do them. Not so in this lecture. These represent more complicated boss-level challenges and necessitate complete mastery of parallel DC circuit properties and a little creativity and thought on your part to achieve the desired results. Take your time and struggle with these problems, and don't tap out too quick. If you can solve these problems, you're tracking. If you can't solve these problems, you do not understand parallel DC circuit properties as well as you think you do. Let's see how it goes. My sincere advice for every single one of these scenarios is to lay out everything you do know about parallel circuits and apply these fundamental properties to the circuit in question. Ideally, you should be able to use the provided clues to make deductions about or to solve for other properties. You will no doubt recall that voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. Additionally, Kirchhoff's current law states that for any node, the summation of incoming currents equals the summation of outgoing currents. In short, what goes in must come out. Finally, power in always equals power out. We can use this fact to solve for other properties or to check our work. Mastery of parallel DC circuit analysis necessitates active participation on your part, and as such, I'm encouraging you to please pause this lecture when asked to do so and attempt example problems on your own. If your answers do not match those illustrated, by all means feel free to rewind the lecture and correct any mistakes you may have made. Our first illustrated example features an unknown voltage source providing 100 milliamperes of source current to a parallel combination of R1, a 270 ohm resistor, and R2, a resistor of unknown magnitude. The only other additional piece of information we're given is that I2 is 40 milliamperes. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2. A Kirchhoff's current law analysis of this circuit demonstrates that source current splits into two paths, I1 and I2. The Kirchhoff's current law equation for this circuit is I source equals I1 plus I2. An algebraic rearrangement of the Kirchhoff's current law for this circuit, solving for I1, demonstrates that I1 is the remaining 60 milliamperes of current. An application of Ohm's law demonstrates that V1 is 16.2 volts. Voltage across elements in parallel is the same. For the circuit, E equals V1, which equals V2, and they all equal 16.2 volts. Total power supplied to the system is equal to supply voltage times source current. Substituting our given values yields 1.62 watts. The power dissipated by resistor 1 is equal to the voltage across it squared divided by resistance. Substituting our given values yields 972 milliwatts. If total power equals P1 plus P2, an algebraic rearrangement of this power distribution formula, solving for unknown power P2, demonstrates that P2 is equal to P total minus P1. Substituting our given values yields 648 milliwatts. An application of Ohm's law solving for R2 demonstrates that R2 is the voltage across it divided by the current through it. Substituting our given values demonstrates that R2 is 405 ohms. As a means of checking our work, the total resistance of R1 and R2 in parallel is 162 ohms. Solving for source current, where source current is equal to supply voltage divided by total resistance, does indeed yield 100 milliamperes. I've got a reasonable degree of confidence these answers are correct, and we can move on to the next illustrated example. Our next illustrated example features an unknown voltage source providing power to a parallel combination of R1, an unknown resistor, and R2, a 400 ohm resistor. It is additionally known that the total resistance seen by the source is 300 ohms, and the power dissipated by the second component is 1 watt. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2. Kirchhoff's current law. Source current splits into two paths. For this circuit, I source equals I1 plus I2. Finally, power in equals power out. For this circuit, power total equals P1 plus P2. You will no doubt recall that power dissipated by the second element is equal to V2 squared divided by R2. An algebraic rearrangement of this formula solving for V2 demonstrates that V2 is 20 volts. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2, and they all equal 20 volts. Source current is equal to supply voltage divided by total resistance. Substituting our given values yields 66.7 milliamperes. I2 equals V2 over R2. Substituting our given values yields 50 milliamperes. An algebraic rearrangement of the Kirchhoff's current law equation for this particular circuit solving for I1 demonstrates that I1 is equal to source current minus I2. Substituting our given values yields the remaining 16.7 milliamperes of current. R1 equals V1 over I1. Substituting our given values yields 1.2 kiloohms. P1 equals I1 squared times R1. Substituting our given values yields 333.3 milliwatts. Power total equals P1 plus P2. Substituting our given values yields roughly 1.3 watts. As a means of checking our work, power total is also equal to supply voltage times source current. Substituting our given values similarly yields 1.3 watts. I've got a reasonable degree of confidence our answers are correct, and we move on to the next illustrated example. Our next illustrated example features a voltage source of unknown magnitude and a parallel combination of R1, an 800 ohm resistor, R2, a 120 ohm resistor, and R3, a 480 ohm resistor. An ammeter installed in this circuit indicates 625 milliamperes of current in the indicated direction. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own.